Imagine waking up and realizing gravity just gave up. Yep, everything's floating, including your cat. So, you've woken up, stumbled to the kitchen outside. The birds are chirping. You check your phone for the news. Before we float away, hit like, subscribe, and tell us what world-ending question you want next. Well, that's a bit of a pickle, isn't it? Can we actually do something about this? The universe, it turns out, is a rather messy place. Real-life, very serious people in labs and observatories spend their entire careers looking for these potential party crashers. It's about physics, patience, and a whole lot of careful planning. To understand how to stop an asteroid, you first need to appreciate why it's so determined to hit us in the first place. It's not personal, it's just physics. And the physics of our solar system is a beautiful but sometimes dangerous cosmic dance. Everything in the solar system is in a constant state of falling. Sir Isaac Newton figured this out centuries ago. He realized that the same force pulling an apple to the ground also keeps the moon locked in orbit around the Earth. The secret is sideways motion. If you have enough forward momentum as you fall towards a massive object like the sun, you continuously miss it. That, in a nutshell, is an orbit. A perpetual fall, perfectly balanced. For billions of years, most asteroids have been playing by these rules, happily orbiting in designated zones. The main asteroid belt, a vast cosmic quarry between Mars and Jupiter, and the even more distant Kuiper belt, way out past Neptune. These are the relatively safe, stable neighborhoods of the solar system. But the solar system isn't always stable. Sometimes an asteroid gets a fateful nudge, perhaps a close pass with another rock, or more likely, a powerful gravitational kick from a giant planet like Jupiter. Its immense gravity creates unstable zones called resonances, acting like a cosmic slingshot that can eject an asteroid from its comfortable home. Suddenly, this once predictable rock is sent tumbling onto a new, chaotic trajectory. A path that might, just might, intersect with the lane our own planet Earth is running in. It's like a rogue driver suddenly swerving into your lane on the motorway. The key difference is that this car is several kilometers wide, weighs billions of tons, and is traveling at about 20 kilometers per second. That's fast enough to cross the Atlantic Ocean in under 5 minutes. And here's the crux of the problem. You can't just jump out of the way. Our planet is stuck on its track, bound by the same laws of gravity. We have a confirmed date at a very specific point in space and time. So if we can't move the Earth, we're going to have to find a way to move the asteroid. We need to give it a nudge ever so slightly, changing its course just enough so that when we arrive at that cosmic intersection, it's already long gone. So how do we even know one of these cosmic menaces is coming for us? In the vast, silent darkness between the planets, there are millions of asteroids. Most are harmlessly circling the sun, minding their own business. But some have orbits that cross our own path, and it's our job to keep a very, very close watch. The search begins with automated sky surveys. Powerful telescopes, like the Vera C. Rubin Observatory, systematically take pictures of the same patch of sky night after night. Sophisticated software then compares these images, looking for anything that moves. Mostly, the stars stay put. But occasionally, a tiny dot of light shifts between pictures. This is the first clue. This initial detection triggers an alert, and astronomers around the world spring into action. The data is sent to the Minor Planet Center, the global clearinghouse for all things that move in the night sky. A single observation isn't enough. We need confirmation. Telescopes pivot to get a better look. They measure its brightness to estimate its size, though this is tricky as a dark, large object can look as dim as a bright, small one. They analyze the reflected sunlight to determine its composition. Is it solid rock, a chunk of metal, or a loose pile of rubble? Powerful radar arrays can even bounce radio waves off it, giving us a precise measurement of its size, shape, and how fast it's spinning. Each new data point, every single observation from every telescope, is fed into powerful computers. They calculate the object's trajectory, refining its orbital path. Early on, the predictions are fuzzy, yielding a wide cone of uncertainty where the asteroid might be in the future. For weeks, maybe months, Earth remains safely outside this cone. But as more data comes in, the cone narrows, and one day, the model spits out a number. It's 100%. There's no ambiguity, no margin for error. The calculations are checked, double-checked, and triple-checked by independent teams. The conclusion is inescapable. Impact is certain. In our hyper-connected world, a secret of this magnitude can't be kept for long. It would likely leak out, first as a rumour on an astronomy forum, then picked up by a sharp-eyed science journalist. And then, suddenly, it's everywhere. The biggest news story in human history. Panic would be the first reaction, but it would have to be followed by purpose. The United Nations would convene an emergency session. Old rivalries would be set aside. A planetary defense coalition would be formed, uniting the world's nations against a common cosmic enemy. The scientists would be brought before world leaders to explain the situation in simple, direct terms. No jargon, no academic hedging, just the cold, hard facts. They would explain the asteroid's size, let's say 10 kilometers across, a mountain of rock and iron similar in scale to the one that wiped out the dinosaurs. They would show the impact point, the time until arrival, and the devastating consequences. A blast equivalent to billions of nuclear bombs. A global firestorm, followed by an impact winter that would block out the sun for years, causing global crop failures and the collapse of ecosystems. It would be an extinction-level event. The world would be presented with a choice. Not whether to act, but how. The era of denial and debate would be over. The era of action would have to begin. Humanity's greatest challenge would demand its greatest collaboration. The first and most sensible option on the table, especially with years of lead time, would not involve giant explosions. Hollywood loves a good bang, but real-world physicists are a bit more cautious. Blowing up a 10-kilometer asteroid might just turn one giant bullet into 1,000 smaller ones, all still heading for Earth. The goal isn't to destroy it, but to nudge it. This is the kinetic impactor. You build a spacecraft, essentially a big, dumb, heavy projectile, and you slam it into the asteroid at incredible speed. The impact transfers momentum, changing the asteroid's velocity by a tiny amount. It sounds small, but over years, that tiny nudge adds up to thousands, then millions of kilometers of difference. We know this works. NASA's DART mission successfully tested this very idea in 2022, altering the orbit of a small asteroid moonlet. For a real planet killer, however, the scale would be immense. We wouldn't send just one. We'd send a fleet of impactors, a coordinated wave of spacecraft built and launched by nations all over the world. Each one would be a silent, lonely collision in the dark, a precisely calculated push upon which the fate of our world depends. But what if we don't have the luxury of decades? What if our first and only warning comes when an asteroid is already looming in our cosmic neighborhood, just a year or two from impact? In such a terrifyingly short time frame, the gentle nudge of a kinetic impactor simply won't be enough. The change in velocity required is too great, the time too short. In that case, mission planners would grimly turn to the second page of their playbook, the nuclear option. The most mature version of this plan is a standoff detonation. The warhead wouldn't strike the asteroid directly. Instead, it would explode at a precisely calculated distance. A fraction of a second later, a torrent of X-rays and neutrons would slam into the asteroid's surface, flash heating the rock into a super-hot plasma. This vaporized material erupting outwards acts like a powerful rocket engine, giving the asteroid a firm, decisive shove. But the risks are enormous. What if the standoff push isn't enough? The alternative, a direct surface or subsurface blast, is far more powerful but infinitely more dangerous. Many asteroids aren't solid boulders. They're fragile rubble piles, loose collections of rock and dust held together by weak gravity. A direct nuclear blast might not push it. It might simply shatter it, turning one giant bullet into a shotgun blast of city-killing fragments, many of which could still be on a collision course with Earth. To avoid such a catastrophe, a precursor mission would be absolutely essential. We would need to send a scout ahead to map the asteroid's shape, spin, and most importantly, its internal structure. We must know if we're dealing with solid iron or a pile of gravel before we even think about pressing the big red button. Thankfully, brute force isn't our only idea. If we have more time, one of the most elegant concepts in planetary defense comes into play: the gravity tractor. It sounds like science fiction, but the physics are simple. You park a heavy spacecraft nearby and just hover. The ship's minuscule gravitational pull, the same force that keeps your feet on the ground, ever so gently tugs on the asteroid. By constantly firing its own thrusters to maintain its position, the spacecraft leads the asteroid inch by inch onto a new, safe path. The key word here is gently. The process is incredibly slow. It requires decades of advance warning and a spacecraft with an extremely efficient, long-lasting propulsion system, like an ion drive that can operate for years on end. But its beauty is its absolute control. There is zero risk of fragmenting the rock. It's the ultimate cosmic tow truck, offering a level of precision and safety no other method can match. Then there's laser ablation, the futuristic option, straight from the pages of classic sci-fi. The principle is similar to a standoff nuclear blast, but far more controlled. You focus a powerful laser onto a small spot on the asteroid, heating it until the rock itself vaporizes. This jet of escaping gas acts as a continuous tiny rocket, steadily pushing the asteroid. The challenge is one of scale. We don't yet have a laser powerful enough that can be mounted on a spacecraft and powered in deep space. But with a decade or two of focused research into high-efficiency solar arrays and laser technology, it's not outside the realm of possibility. But what if all our attempts fail? If deflection is off the table, the focus must shift, grimly, from prevention to survival. The logistics of predicting the impact zone, coordinating a global response, and potentially evacuating millions would be staggering. It's a scenario that underscores why developing these deflection technologies isn't just an interesting engineering problem. It's a critical investment in our future. So we stand at a crossroads, not in reality today, but in this hypothetical future. We have telescopes to see danger, the intelligence to understand it, and the blueprints to fight back. The question is not capability, but will. Invest in telescopes, fund the research, build the systems before the alarm bell rings. The story of humanity versus the planet killer is not about asteroids, it's about us. It's about foresight, cooperation, and rising to the challenge. Thanks for watching IfVerse. See you next time, if the laws of physics still exist.